about the same. Yeah. I came in at 9 just to like get here early before it started getting slushy. And there was no one in the parking lot. I could actually park wherever I wanted, which was nice. In the 11 o'clock class, we had 3 people in the beginning, but then a few other people came in during class. That's an option, yeah. So I keep getting mixed reports on what's coming next, but yeah, it sounds like we might get more.
In general, when it gets to snow around here, the weather can't be trusted.
Yeah, it's. Eventually. I heard a lot of forecasts.
Your best bet is a 24-hour forecast.
Yeah.
Beyond that is not reliable.
And it's easier back east because you can follow the jet stream all the way across the country, and you pretty much can nail down what's going to happen, like a few days out at least. Here it's much trickier. So I did not want to cancel this class in particular because we didn't have class on Monday, and I didn't want to go a whole week without meeting. So thank you for coming. Echoing comments I made earlier in the week, right? Don't ever take chances if you feel like you can't get in here safely or something like that. These are always being recorded and posted, so you know you can sit around and make some hot cocoa and watch some 222 videos. But yeah, so I wanted to go through some tree operations today. And I wanted to look at deletion in particular because that's probably the sketchiest one. I wanted to compare iterative versus recursive versions of some of these functions. And I'm going to post an ODP tomorrow morning, so I wanted to go over what you need to do that. And we'll see where that gets us. And then if there's time, I want to start talking about some other things related to trees. In particular, I want to talk about tries. But if we don't do that today, we'll get to it next week. So any questions first before we start? Yeah. I've seen you write recursion. You wrote it perfectly.
I felt like it was wrong. It worked, but I felt like I did it wrong.
That's probably a good indication that you're doing something right. So let's look at some recursive code.
I guess I just don't understand how it works when you call it, but then right after you return. I mean, I know it waits until the function completes to proceed to the next instruction.
Mm-hmm.
But how does that work when it gets like 3 or 4 layers into the
Magic. So let's think about linked lists, and let's forget about sentinel nodes for this, okay? So we have a linked list. It's got these nodes, and the first node, so LL's the pointer to our first node, and that's got our first data value, 10. That points to a 15, points to a 25, and it goes on and on and on. And we want to write a function called print, which takes a pointer to the first node of the list. And we know how to do this iteratively. We make a temporary pointer, set it equal to LL. We print out its data value. If its next value is not null, we set it to its next value. We go back to the top of our loop. Print that node's data value. If the next value is not null, set temp equal to that. Go back to the top of the loop and keep going. But we can also do this recursively as follows. So if LL is null, let's just return. Okay, if you ask me to print an empty list, I'm not going to print anything. I'm just going to return and say I'm done. Otherwise, let's print out its data. So I'll use a printf and print the node, the data field of the thing that LL is pointing to. that prints the first node in our list. To print the rest of the list, I'm going to call my handy-dandy print routine. And I'm going to give it the address of the second node in our list and say, print this list for me. And that's going to print my entire list. Okay, that's classic recursion. So we've got a base case. This is what stops us from just calling ourselves endlessly and never quitting. So when we try to print a list that's empty, we just return there's nothing to do. But if there's anything in the list, we're going to print out the data value of the first node. And then we're going to print all the remaining nodes by calling our print routine. Right? But of course, this is our print routine that we're writing. That's the recursive part. But that's a totally classic example of a recursive algorithm. Right? And I don't know why it works. It works. I don't know how to explain it any better than that. If we believe that print will print all the data in a linked list, then we can convince ourselves that all of this works. Right? But you kind of need to believe up front that this is going to work. And if you believe that this will work, then those 3 lines will work to print the entire list. But you're actually doing a mathematical induction, right? You're proving it for a list of length 0, because that's going to fire this base case. And if this works for a list containing n nodes, then this will work for a list containing n plus 1 nodes. Because this will be printing a list of n nodes, which we're assuming is the case. And this will print the first node, and then we print the remaining nodes. And so our list of n plus 1 nodes works. Therefore, our proposition that this works for a list of n nodes is true for all n bigger than or equal to 0. But it should tickle your brain somewhat. Okay. So yeah, it does. So this is the recursive version of while LL is not null, printf data LL equals LL next. Which one's more efficient? The iterative one's going to be a lot more efficient. Because a while statement is a go-to, it's a branch. It's a go-to in pick assembly language. This is a call, so it's pushing things onto the stack. In C, it's pushing a lot of things onto the stack, like all of our local variables, and then changing the PC to go back to the beginning of this routine. If you tried to print a list containing 1 billion nodes, this will probably blow up, because you're calling yourself so many times, and you have to remember all of those calls that you'll run out of stack space. There's really no limit to how long a list it will manage, because we're not doing any housekeeping each time that we go back to our while.
So if the while is more efficient, what's recursion better at?
Once you're kind of in the zone of thinking recursively, this may be what comes to mind first. Right? How do I print everything in a list? Well, print the first thing and then print everything else. Right? Now, that's not how we normally think of as programmers. We think of print the first thing, move to the second thing, print that, move to the next thing, keep going until it's null. But this is a different mindset. Right? How do you sort a list of 100 numbers? Well, let's sort this list of 50, let's sort this list of 50, and then let's put those 2 lists together so that they're still sorted. Right? That's something called a merge sort, and it's recursive, and it's very efficient, and it's very easy to code. Because how do you sort this list of 50? Well, break it into 2 lists of 25, sort this, put them together. And how do you sort those? Well, you call your sort routine again, right? But you call it on a set of 12 and a set of 13. You put them together. And the only thing you really have to do is write code to take two sorted lists and interleave them correctly so that they're still sorted. But you end up with a general sort that works on anything. So we're going to look at iterative and recursive algorithms for searching a binary tree and for inserting. And with the insert in particular, you'll probably see a case where recursion is going to be a lot simpler. Thinking about it recursively is going to be less edge cases to deal with than iteratively. But in general, recursion is basically taking a problem and finding the solution in terms of smaller versions of that problem. So Towers of Hanoi with 8 disks, if you can solve it for 7 disks, it's easy to solve it for 8. Right? Take your 7 disks, move it here, move your biggest disk there, take those 7 disks, move it there. So recursion's best suited where the solution kind of presents itself in terms of solutions of smaller problems. And a lot of the stuff we do in trees will look like that. Now, I wouldn't write a linked list traversal recursively. There's no reason to do it, right? This code is very straightforward. It's more efficient, and there is a danger of blowing up, right? The number of times you call yourself is order n, where n is the number of things in the list. But nonetheless, you could do it like this, right? You could make a recursive linked list insert routine, which says if your number is smaller than the first node, make the first node your new node and point to the rest of your list. Otherwise, insert your number in that list that comes after the first node, right, by calling the insert routine recursively. So it's a really good question, and I don't have a definitive answer for it, but it's a good question to keep examining as we're going through looking at recursive code. And you won't even know when it happens, but at some point it will click over to the other side, and it'll seem pretty natural. All right, good. Other questions, comments? So let's look at trees. So let's search for a number inside a tree. And let's do this iteratively. So how do we do this? We start off with the root node. And if that root node's data is the number that we're looking for, then we can say we found our number. So here's temp. And let's say we're searching for 30. All right, if it's not the root data that we're looking for, we need to search either the right or the left subtree. We need to move either down to the left or down to the right. And it depends on how our number compares to the root data. So if our number is less than the root, if our number is less than temp arrow data, move temp down to be the right child. Otherwise, move down to the left. So in this case, we're looking for a 30 that's bigger than 20, so we'll move temp down to here. And then we want to basically come back up to here and see if the new temp's data matches ours. And it doesn't, and our number is less than temp, so we're going to change temp to be, I got my right and left reversed. So if our number is smaller, then we should move to the left, otherwise we move to the right. So 30 is smaller than 50, so we'll set temp to temp arrow left, and we'll come back up here to the top, and if temp data equals num, which it does, we'll say it was found. But if we're searching for something that's not found, so we're searching for 31, 31 is not less than 30, so we're going to move temp to temp arrow right, which is null. And when we come up here, we can't check temp arrow data, because if temp's null, that's going to seg fault us. So this can all sit inside a while loop. Well, temp is not null. And if we come out of the while loop, it means we didn't return, but we got to a place where temp is null, so our number was not found. So it's not found. So that's an iterative search. There's no recursion in there, there's just a while loop. And it works exactly the way that we would search a tree ourselves. We'd start here, whatever we're looking for, we come down to either the left or the right, and we keep coming down and following our way through the tree until we find our number, or we get to a leaf and it's not equal to our number. And when we move left or right, we get to a null. We know our number is not in the tree. So that's an iterative solution. Let's look at the recursive version. So how do we do this recursively? Well, again, if the root is equal to our number, then we can just say we're found. But if we're looking for the number 30 or 31 in this tree and root is pointing to a 20, we know that 30 is bigger than 20. The only place that our number could possibly be is somewhere in this right subtree, right? It can't be over here to the left because we're searching for something bigger than the root. And everything to the left of the root is smaller than it. So if we're looking for something bigger than the root, it's got to be somewhere in this right subtree if it's anywhere. So if root data is less than our number, so num can only be in the right subtree. Well, let's just search the right subtree. So search root arrow right for our number. And if it's found in the right subtree, then it was found in the original tree. And if it's not found in the right subtree, it's not found in the original tree. Because the only place it can be is in that right subtree. So we can simply return whatever we get from this call to search. And the same thing on the left. So if the root data is bigger than our number can only be in the left subtree. So search that left subtree for our number and return what that search call gave us to tell whether or not the thing's in our tree. And the danger here is that as we continue doing this, we're going to search for 31 in this subtree. 31 is smaller than 40, so we're going to search for 31 in this subtree. 31 is bigger than 30, so we're going to search for 31 in this subtree. And when we call search with a root that's equal to null, this is going to blow up when we try to find the data value at the root. So we're missing an edge case here, which is the case where the tree we're searching is null. So put that in. If root is null, then it's not found. So there's a 4-step recursive search function. See if the root's null. If it is, it's not found. See if the root matches our data. If it is, then it is found. Otherwise, search either the left or right subtree and return what value you get from that search. So we don't have to loop, we don't have to keep track of nodes and work our way through and so on and so forth. We're just trusting the search function to do the right thing. Yeah?
So in this case, root is null error next, because we already moved when we did the recursive call.
So there is no root arrow next. There could be a root arrow left or right.
Yeah, sorry, that's what
But we could do something like, I mean, we could do this that way. Down here, instead of calling search root arrow right, we could say if root arrow right is null, then return not found. Otherwise, search root arrow right for our number. And same thing here with root arrow left. And then we would never recursively call search where root was null. But we still might have the situation where the original tree we're searching is null. And we'd need to somewhere check to make sure we don't call search on a null tree. So we'd need this in here either anyway, or we'd need it like in our main program. And the lower general rule, I don't know if this is accurate or not, but my general feeling is the lower you can make this base case, the better. The further down the possible recursive tree you can make the base case, the simpler your code tends to be. Probably not always, but that's the sense coming out here. Yeah?
Would it be redundant to when it returns the whatever it gets from the recursion?
Mm-hmm.
Would it be redundant in the main function to have it check if it's equal and then it's success if it is, or?
Check if what's equal.
Because aren't you returning? Like, I guess I don't understand what you're returning from the when you go through the search again.
So let's just say that 0 equals not found. 1 equals found.
Oh, I see. So
So it's returning an int.
at some layer it'll hit that if it equals found.
At some point after we've called ourselves n times, right, we may run out of nodes, in which case we'll return a 0, or we may actually find the data, in which case we return a 1. And however we got to that point, all of those calls to search are going to pass back that value that we returned from either here or here, all the way back up to the original caller. Okay, that's the magic of recursion part again.
It's kind of like a line of people.
Mm-hmm.
Guy turns to his right, says, "Go get a bucket of water."
Yes,
Guy turns to his
yes.
right, "Go get a bucket of water."
Yeah,
One of the guys goes, "Get a bucket of water," and then he passes.
yeah, yeah.
Here's the bucket of water.
We should do that. That's a really cool idea. I'm going to do an experiment for this sometime. Maybe not in this class, because we're already down the road to recursion. But yeah, we could do this with a group of people.
Everyone gets snow.
Yeah. Yeah, so I mean, you could take a tree And I could ask you to search it, and you could decide which subtree it's in and hand it to your neighbor. And they could do the same thing and keep doing this until eventually somebody finds it or doesn't find it and then just passes it back all the way. That would be cool. Be a fun video.
Only rule is you can't move your feet.
Yes. Yeah, I like that. Yeah, yeah. That would be good. Yeah. So this if statement, again, is redundant. I don't mind putting it in there because I think it's sort of self-documenting in that way, right? But if the root data is not equal to our number and it's not less than, it's got to be greater than. So I would probably put this in as a comment just to let people know what's going on. So here's an interesting question. We've got an if statement with a call to search. We've got maybe an if statement or not with another call to search. Could we replace these two lines of code with a single line of code that doesn't do any sort of conditional? Doesn't do an if, doesn't do a ternary operator, but somehow gets the same result. It's not exact, but
Yeah, I have to do is check for one of those if cases, and then the ternary spits out one of those or the other.
no ternaries. Yeah. So, and let me change this to a Boolean, whatever that means. But let's think of search as actually returning true or false. So think about this. What is that going to do?
Would it search both and then decide to return one?
It's going to search both. And if either of those returns true, then it's going to return true. If they both return false, then and only then will it return false. And we know that if our number is in the tree, right, if it's at the root, we say it's found. If it's not at the root, but it's in the tree, it's in either the left subtree or the right subtree. So one of these is going to return true. And true ORed with anything is going to be true, so this will return true. The number's in our tree. And if it's not in our tree, it's not in the left or right subtree, both of these will return false. And false or false will be false, so this will return false. So this will functionally give the same result as this pair of if statements.
So the ands and the ors work, what, the 250 concepts?
Yeah, so this is why we have to change this to a Boolean because we can't really OR integers. We could, but I don't want to go down that path. But yeah, if we think of this as returning some kind of truth value, it's found or not found, right? And we have a way to take a Boolean OR of that. We can simply go down both trees and look for it and not bother with our knowledge that if our number is bigger than the root, it's got to be in the right subtree. We can just say, search both trees. Tell me if you find it. But here's an interesting question. How does the efficiency of this compare with the efficiency of that? What do we lose by going down both trees instead of just following the left or the right? Does it make a difference? it twice as long?
Does it make that order one? Like you're searching the entire tree instead of just one?
You're searching the entire tree when you do this. And for one particular call of search, it looks like we're doing twice as much work. We're searching 2 subtrees instead of 1. But remember, each time that we call search, we're going to recurse a bunch of times after that, however many times it takes to get to our number. And in the case where our number is not found in our tree, when we're searching for 31 in this tree up here, we're going to search this entire left subtree and this entire right subtree. And to search this entire subtree, we're going to search this entire left subtree and anything that was on the right. And we're going to have to search this, and we're going to have to search this. And the same thing on the right. We're basically traversing the entire tree. We're checking every single node in the tree to see if it's equal to our data or not. And so this is actually going to come out as something like order n, where n is the number of nodes in the tree. Now, if we follow to the left or the right, come here, come here, come here, the number of times that we have to recurse is really just the depth of that node, which is bounded by the height of the tree, because that's the maximum depth. And the height of a tree, assuming it's well balanced, is on the order of log n. So this is tremendously more efficient than this. And that might not be intuitively obvious, but it surprised me when I saw it at least. But nonetheless, algorithmically, it's perfectly valid, right? And it's recursive, and it takes even fewer lines. All right, so let's think about insertion. So we want to insert a number into a tree. And remember, anytime that we have the potential to change the root of a tree, which is insert or delete, we're going to want to return the possibly new root of that tree, right? Because we don't have sentinels. So we're going to pass in a root and say insert this number, and insert's going to return to us the root of a tree that has that number inserted into it. And most particularly, if root is null to begin with, this is going to have to return the root of a tree containing 1 node, which is the node that has our number in it. So we definitely need to return a pointer to a tree node. So let's insert 11. And we're going to do this iteratively. So we can do something like temp, or let me do current. Current equals root. And we're assuming that your number is not already in the tree. Okay, so your number is not a member of the tree. So start off with a temporary pointer. And let's set current equal to the left or the right child. So if our number is less than current data, set current to the left child. Else, set current to the right child. So we want to insert an 11. 11 is less than 20, so we're going to change current to point to the 10. 11 is bigger than 10, we're going to change current to point to the 12. And we want to do this until we get to a null. So we can say while current is not null. And we'll keep doing this. So 11 is smaller than 12. So we'll set current to the left child of 12, which is null. And now we're at the point where we want to insert our new node. We want the 11 to go right in place of this null. Well, we've figured out where to insert this thing, but we've lost a piece of information we need. We need to know what the previous node was, because this new node, this 11, has got to get tacked on to the node that we came from to get to this null. In other words, this 11 has to be adopted by the prior node we were at. So we need to keep track of the previous node. So we want something like previous equals current before we move current. So now how this is going to work, I'm going to make a new picture of this. So we start off with here's current, and we also set previous to this. Number is less than current data, so change current to the left child. Come back up to our loop. Current is not null, so set previous equal to current. Our number 11 is bigger than current data, so set current equal to current right. Come back up to the top of our loop. Current is not null, so set previous equal to current. And our number is smaller than current data, so set current to current left. Come back to the top of our loop. Current is null, so now we kick out of our loop. So now add our new node as a child of previous. But we still need one more piece of information. We know that 11 should be a child of the previous node, but we don't know if it should go on the left or the right. So we could either compare our data to previous data again, or we could remember our last direction that we came from. So each time that we move through our tree, remember which way we moved the last time. So in this case, last direction would have been left because we moved down to the left. And so now we can do a condition. If last dir is left, then previous left is our new node, else previous right is our new node. And we still have an extra edge case. If root is null, return our new node. So we also need to make a new node somewhere in the beginning here. So do that up front. Make a new node. And in these cases where we've moved down from the root, found a leaf, tacked our new node onto it, we haven't changed the root of the tree, so we can just return the original root. So there's a sloppily drawn insertion routine with no recursion. Right, so make a new node, check the root. If the root's null, return that new node as the root of the tree. Otherwise, make a current pointer, which is initialized to the root, and while that's not null, save it in a previous pointer, move current down to the left or the right, and iterate. And record which the last direction was that you moved down. And then when you're done, because your current node is null, go ahead and set the previous node's left or right child to be your new node and return the original root. All right, so that's doable, that's iterative, but let's look at the recursive version. And the main thing that makes the iterative version a little uncomfortable is that we have to keep track of all this information. We need the previous node, we need to know how we moved from the previous to the current, and we have the edge cases to deal with. So let's do tnode insert root and some number. All right, we need a base case. So if root equals null, make a new node and return it. So that's pretty obvious, right? If you're asked to insert into an empty tree, make a new node, return the new node as the root of the tree. So that's the same base case that we had before. If our number is smaller than the root, right, so there is a root, the tree is not null. If our number is smaller than the root, let's just insert our number into the left subtree using our insert routine. And let's make the root's left child equal to what that insert routine returned, and then return the original root. Otherwise, the new number belongs on the right subtree, somewhere on the right of the root. So let's set the root's right child to the tree we get when we start with the right subtree and insert our number. So there's your whole insert routine. So a base case, if the root's null, make a node, return that node. Otherwise, a recursive call to insert our number into either the left subtree or the right subtree, and have the root's left or right subtree now equal to what we got by doing that insert. And the original root doesn't change. You could, if you allowed the case where your number is not in the tree, then you could just say insert on the left and insert on the right. Maybe. No, I don't think so. That wouldn't work because it will find somewhere to put it. I don't know. It's an interesting question. It feels like it should be symmetric, right? I don't know what the symmetric version of that would be. All right, so divide and conquer, right? Taking a problem, breaking it down into subproblems. So my job is to insert a number into a tree that's this big. Your job is to insert into trees that are only this big. And so if you give me a tree this big and ask me to put a number into it, I'm just going to figure out if it goes in the left subtree or the right subtree. I'm going to hand you that smaller tree and the number and say, hey, put this into this tree for me. You're going to give me back a tree, and I'm going to replace my left or right subtree with what you gave me back. And I didn't have to do any work. That's basically how this is working.
So it's a quick question.
Mm-hmm.
Could you return the whole statement root arrow left equals insert root arrow left comma none, or would that mess everything up?
That would return the left subtree.
Okay.
And you want to return the root of the original, of the new tree. So, but if you wanted to return the left subtree, you could say return parentheses this, and that would return root arrow left.
Okay.
Right, that's valid syntax. What else could you do?
So returning root returns whatever root was before the function call then, right?
Yeah. Because really, the only time that we need to return something is if you're passing me an empty tree, and I'm giving you back a tree that's not empty. Other than an empty tree, when you insert, it never changes the root of the tree, right? Because we're not rebalancing, we're just marching down from the root and then adding as a child of a leaf node. So we could just make this void except for that one case where we have an empty tree, but it turns out that this routine's always going to call itself once with an empty tree. And if it didn't, this wouldn't work.
So with recursion, you can't have void returns.
Yeah, you can. Right, like the recursive print routine, that would be void because it doesn't return anything. But if your recursive function is trying to change your structure somehow, you probably need to be returning it. And this doesn't work, for example, if root is just a global variable, right? If we made root a global instead of passing it as an argument, and we started doing this, well, every time that we made a change, right, it would be losing the old copy of things. It's really the fact that arguments get saved on the stack that makes this viable. And you can trace this in GDB, but it's a little nightmarish. But you could also throw a bunch of print statements in here. And, you know, I'm checking to see if the root is null. I'm checking to see if my number is smaller than the root. Yes, it is. I'm calling insert to insert it into the left and things like that. Trees are a little harder because they're a little hard to print unless you make yourself a nice tree print routine. But you could, you know, print out all the data that's in your tree in the beginning here, do like a in-order traversal or something, and say, you know, just entered insert, here's what the tree looks like right now, and do your traversal on root. And that gives you a bunch of output, but it's not too bad to kind of stare at with some empty sheets of paper and sort of figure out what's calling what and how the recursion's going down and how it's coming back up. That's probably more useful than GDB at this point, right? GDB will be good if you're having some particular problem, something's null and it shouldn't be. But to understand the overall flow, something higher level like print statements isn't bad. Other questions, comments? All right, let me talk about your ODP, which I'll post tomorrow morning, and then we'll take a break, and then we'll talk about deletion. But your ODP is a piece of what you're going to have to do to delete a node, but it's just one piece of it. et cetera, et cetera. So here's what your ODP is going to do. I'm going to give you a tree, and I'm going to ask you to find the largest node in the left subtree and return that node's integer value. Okay, so it's a piece of how we would do our deletion. So I'm going to give you a tree like this. I'll give you the address of the root, and your goal is to explore this tree and find the largest node in the left subtree, in this case 15. And I'm not going to give you an empty tree, and I'm not going to give you a tree that has no left child. So your tree is always going to have something on the left other than null, just for the sake of this ODP. So your algorithm is something like temp equals root arrow left. So that's the left subtree. And we know this is not null. And then while temp arrow right is not null, just move down to the right. And when you get down to a point where temp's right child is null, that's the largest node. So you can just return temp arrow data. So start off, temp is the root of the left subtree, and while there's something on the right, move to the right. While there's something on the right, move to the right. When there's nothing on the right anymore, you're at the largest node, just return its data value. But it's a chance to play around with code to do these things, moving around through a tree and so on and so forth. And the assessment code will call your function with different trees and ask you to do this. But there'll always be some subtree on the left for the ODP. All right, let's take a 5-minute break, and then let's look at the details of deleting a node from a tree. And we'll use this as a piece of it, but there's going to be a number of special cases to deal with.